We'll now dig into control charts, including the X bar and the R charts, as well as interpreting these charts. And we will not do any calculations in this chapter. Rather, we'll just focus on interpreting the outputs. As we highlighted in the previous section, control charts focus on establishing the stability, meaning the control of a process. A process needs to first be stable before we can check it against customer expectations. Another way to think about that is it's not even worth checking the process against the voice of the customer if it's not yet stable. A control chart is a statistic that's plotted over time. We can plot the mean, the X bar, to see if the average is stable, and we can also plot the range to assess if the variability is stable. And we'll clarify these later in this chapter. Here's an example of a control chart. On the x-axis, we have time, and then the y-axis is the statistic, the X bar or the R. And we see the upper control limit, this upper benchmark, and the lower control limit, the lower benchmark. These will help us assess the stability of the statistic. And we'll learn more about how to calculate and interpret these control limits later in this section. And then finally, we see the average, the middle line. This will further help us assess the stability of the statistic. In general, control charts help us to identify any assignable, meaning non-random variation. Again, assignable means that we can attach it to a cause, a reason. So assignable is not good. If there is assignable variation, meaning an underlying cause, we want to stop and fix that cause. So ideally, we just want to see natural, meaning random variation with no signs of assignable variation. In that case, our process is stable. It's in control. Some practitioners refer to this as the voice of the process. The process is telling us if it's stable, which is good, or it's not stable, which is not good. The X bar chart plots the average, the mean, over time. X bar is written as an X with a bar on top. That stands for the sample mean. And then the R chart represents the variability, the range. It's simply the highest value minus the lowest value. And yes, a standard deviation is a better measure of variability. However, the range is just much easier to calculate, which helped years ago when computers or even calculators were not readily available on the production floor. What do we want to see on these charts? Well, ideally, we want no pattern. The data should look random, and then all points should be within control limits. In this X bar chart, for instance, the points look, well, relatively random, but we do see 1 point beyond the upper control limit, the UCL, and that doesn't look good. And we also see 1 point below the lower control limit, the LCL. That's also not good. So this X bar chart on its own would alert us to problems with the process stability, the control of the process. Let's also look at the R chart, and we'll discuss why we need to look at both the X bar chart and the R chart later in this section. But is this R chart random and well within control limits? Well, there are no points outside of either control limit, but there are some problems with randomness. We see 5 consecutive points nearing the upper control limit. That's probably not random, so that's not good. And we actually see 8 consecutive points above the center line. That's also probably not random, which is again not good. So, to explain, it's highly unlikely, at least statistically, that a process with only random natural variation would have either of those two issues. So, for this process, we see issues with both the X bar chart and the R chart. So, we'd want to improve the process as soon as possible, such as via Lean and/or Six Sigma. Let's consider an example with appointment times at a large medical clinic. We don't want these appointment times to be too long. That creates delays and our patients have to wait. But if the appointments are too short, then the patients may not feel like they're getting sufficient care. So each hour will randomly sample the duration of 4 appointments. So each hour we'll look at 4 appointment times, hour after hour. So hour 1, hour 2, hour 3, and then so forth throughout the day. And then for each sample, we want to calculate a mean, the X bar. And we also want to calculate the range, the R. So for hour 1, the mean will add up the 4 observations, 26 plus 24 plus 30 plus 27. That's 107, then divided by 4, and that is 26.75. So X bar 1, the average of the first 4 observations is 26.75 minutes. And then the range will be the highest value, which looks to be 30, minus the lowest value, which is 24. So R1 is 6. The range for the first hour is 6 minutes. For hour 2, the mean would be 23 plus 24 plus 26 plus 28. So that's 101. 101 divided by 4 is 25.25. So X bar 2 is 25.25, the mean for sample 2. And then the range is the highest value minus the lowest value. So 28 minus 23, 28 minus 23 is 5. So R2, the range for sample 2 is 5. And we keep calculating the X bars and the R's for each hour, for each sample. So we have all of our X bars and our R's for each sample. And now we'll actually calculate a mean of the X bars and a mean of the ranges. So first, the average of the X bars, the mean of the means. We'll call it X bar, the mean of the X bars. So we'll add up all the X bars, 26.75 plus 25.25, 27.25, 25.25, 24.25, and 27.25. We can add those up and divide by 6, and that is 26. The mean of our means, the X bar, is 26 minutes. And then we also want to calculate the mean of the ranges, the average range. So that's 6 plus 5 plus 3 plus 8 plus 4 plus 7. So that's 33. And then we divide by 6 observations, and that is 5.5. So R bar, the average range is 5.5 minutes. So at this point, we can now calculate the control limits for our X bar chart and our R chart. And again, you're not responsible for these calculations, at least in this class, but you still may want to follow along. For the X bar chart, we can calculate the upper control limit, which is X bar plus A2 R bar. So we just calculated X bar and R bar. We need the A2, and that comes from this parameter table. And our sample size, N, is 4. Every hour we sample 4 appointments. So in this case, A2 is 0.73. So our calculation for the upper control limit is 26 plus 0.73 times 5.5. 26 is X bar bar, 5.5 is the R bar, and 0.73 comes from the parameter table. So that's 30.02, technically minutes. And then the lower control limit is almost the same, except for that minus sign. So we take 26 minus 0.73 times 5.5, and that equals 21.99. The lower control limit is 21.99 minutes. So we have our upper and lower control limits for the X bar chart. For the R chart, the calculations are a bit easier. The upper control limit is D4 R bar. D4 again comes from that same table, same sample size. So in this case, D4 is 2.28. So our upper control limit is 2.28 times R bar, 5.5. So that's 12.54 for the upper control limit. Then the lower control limit is D3 times R bar. Again, D3 coming from that table, same sample size. So our D3 is 0, which makes the calculation easy. 0 times 5.5 is 0. So we have our upper and lower control limits for the R chart now. So for the X bar chart, we now have that upper control limit at 30.02. We also have the center line here at 26, which is X bar bar. And then we have the lower control limit at 21.99. So we have our control limits, the center line, and then we just plot the X bars, 26.75, 25.25, 27.25. We just plot those relative to the upper and lower control limits and the center line. And the R chart will be similar. We have our upper control limit at 12.54, and then we have our center line here at R bar, which is 5.5, and then we have our lower control limit, which is 0. And then we'll just plot our R's, 653,847, 653,847 relative to the upper and lower control limits, and then that center line. Let's now interpret these charts. So looking at the X bar chart, we see no points outside of control limits, so that's good. They look to be relatively random, and that's also good. So randomness within control limits, that looks good. And then the R chart also looks good. No points outside of control limits, that's good. And they seem to be random, also good. So random within control limits looks good. So since all we see is random variation within control limits on both the X bar chart and the R chart, this process looks to be stable, meaning it's in control. There's no sign of assignable variation, which means no assignable cause. That's great news. Let's next learn more about interpreting control charts to specifically determine if variation is assignable, non-random. That's bad. Assignable variation means assignable cause. And these are called run tests. Run tests. And for a stable, in-control process, ideally, we'd like to see data that's random, meaning no pattern, and then also well within control limits. And we can visualize this with training a new teenage driver. I have really had my fair share of that. Before we let them go out on the road, we'd like to take them to maybe a large open parking lot to allow them to get their driving to a stable point, in control. And maybe then and only then we could take them to a empty or at least not busy road. But again, how do we really know if their driving is stable, if it's in control? Consider the road itself. What helps us to differentiate stable, meaning in control driving, that would be natural variation, versus unstable, out of control driving, that would be assignable or non-random variation. Well, to start, we definitely don't want them crossing the yellow line on the left side of the road. And if we think of the left side as the top of our control chart, this represents the upper control limit, the UCL. But we also don't want them crossing the white line on the right side of the road. And this represents our lower control limit, the LCL. And then finally, we'd also like them to stay mostly in the center and between the yellow and the white lines. That middle is the center line. We can't really see it on an actual road, but we can certainly imagine. For natural variation, we'd like the car to stay well in between the yellow line, the upper control limit, and the white line, the lower control limit, staying reasonably close to the center line, the middle. So random variation well within control limits, the yellow and white lines. Recognize that the car, though, won't always stay perfectly in the middle, but it should be reasonably close. Again, natural variation means randomness, no assignable cause. What if our driver crossed over the white line to the right, the LCL? So we'd probably have them pull over and practice in a safe area to gain control. Same with the yellow line to the left, the UCL. Pull it over, buddy. You're not stable. We need to practice some more. So crossing either the LCL or the UCL, even just once, is a sign of assignable, meaning non-random variation. And that's not good. Suppose that our driver stays within control limits, but continually drifts to the right towards that lower control limit, or maybe to the left towards the upper control limit. We'll call this a trend. Again, not good. It suggests assignable cause. We should stop and fix that underlying cause to remove the assignable variation. Suppose that our driver continually hugs the right side or the left side of the road, though without crossing the yellow or white line. Again, not good. That's not random. It's not stable. We would call this bias. And again, we need to fix this to resolve the underlying assignable variation, that assignable cause. One more. Suppose that our driver stays within control limits, but swerves from one side to the other over and over again. That definitely doesn't look good. That is not random. We'll call that erratic. And it's likely assignable variation that needs to be fixed. Again, we'd like our driver to stay well within control limits, the upper control limit, the yellow line to the left, and then the lower control limit, the white line to the right, relatively within the center of the road, that center line, recognizing that there will be some subtle minor shifts. Back to our control charts now. As we just visualized, we want a random pattern well within control limits. If not, the process is not stable. It's not in control. And we'd want to stop and fix it, such as via lean and or Six Sigma. And these concerns hold for both the X bar chart and or the R chart. Any concerns on one or both charts, and we need to fix the process. And our concerns, as we just saw, are non-randomness. So for example, any points outside of control limits, either the UCL and or the LCL, that would be problematic and we need to stop and fix the process. And then we also saw the idea of a trend, 5+ consecutive points moving up or moving down. That's also a sign of non-randomness. And then bias, 5+ consecutive points below or above the center line. That would be also a sign of non-randomness. And then finally, erratic behavior, where we have these significant swings from side to side. That would also be non-random. Any non-random issues on the X bar chart and or the R chart, we stop and fix the process. Those concerns may seem to be subject to some interpretation, but there are more formalized tests, including the Western Electric run tests. But we'll stick to our ballpark rules for this class, though. And besides, managerial experience, insight, and discretion are always an important part of running an organization. Revisiting our medical clinic, the X-bar chart displays natural variation well within control limits. And same for the R chart. Also, natural variation well within control limits. So this process seems to be stable, at least so far. Let's brainstorm why we need both charts, the X-bar chart and the R chart, because we'll use these charts together to identify and diagnose issues. These charts indicate different potential sources of variation. The X-bar chart is the average tendency, which relates to accuracy. And the R chart is the dispersion of this average tendency. That would be tightness or precision. So we can consider shooting at a target where ideally we'd like to hit the bullseye, or at least be near and around the bullseye. Suppose that our first shot hits the bullseye and the second shot just misses. The next shot also misses, but it's worse, and to the complete opposite side. The next shot is even worse, again, switching to another side. And then each continual shot is random, but keeps getting farther and farther away from the bullseye, but all around the target. In this case, our variation, specifically the precision, is getting worse. Our shots overall average to a bullseye, which is good, but they're all over the target and getting farther out, which is bad. Something is clearly wrong. And then the R chart would help us see that, likely via an upward trend in the R data. The distribution is still centered, but it's getting wider and wider, more dispersed. Let's consider a second example. Suppose that our first shot again hits the bullseye. The second shot just misses. It's towards the upper right. The third shot hits even farther towards the upper right. And then our fourth and every ensuing shot mostly continues this pattern farther and farther away towards the upper right. In this case, our variation, specifically the accuracy, is getting worse. Our shot grouping is tight, which is good, but it's drifting upwards to the right, and that's bad. So something's wrong again, and this time the X bar chart would help us see that, likely via an upward trend in the X bar data. The distribution is drifting upward. So the X bar chart and the R chart are used in conjunction to assess different aspects of variation. So we assess both to determine any assignable cause in our process. And if a process does show assignable cause on the X bar chart and or the R chart, we'd want to stop and fix the process. And maybe our frontline workers can diagnose it quickly via lean based on their expertise and experience, or maybe we need to throw Six Sigma at it for a more in-depth analysis and fix. Regardless, we can hopefully then apply prevention techniques to stop the cause from recurring.